Hello, everyone, and thank you for joining us today. Welcome to Megger's Virtual Substation Best Practices Seminar. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentations and supporting you on any technical issues or questions for our presenters. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of each presentation. Today, we will have two separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. The presenter for our first segment today is Sanket Bolar, Applications Engineer. To assist with the question and answer session, we will have two panelists joining us today, Kenneth Petrov, Transformer Product Manager, and Dinesh Chajer, Technical Support Group Manager. All right, let's go ahead and get started. Thank you so much for joining us today, Sanket.
Thanks, Mike. Hello, everyone. So in the first session, we'll be talking about transformer insulation health assessment through power factor testing. We'll go over the following sections in this presentation. We'll start off by talking a little bit about transformer insulation, why there is a need to test transformer insulation. Then we'll get into the fundamentals, we'll get into the basics, we'll talk about capacitance and power factor, try to get an understanding of those terms. Then we'll talk about power factor testing. We'll start off with the theory, we'll talk about how to do the test, we'll look at some test results, how to validate those test results, and then we'll get into variable frequency power factor testing, also called dielectric frequency response. We'll talk about that, and then eventually we'll talk about some best practices, and then we'll conclude by talking about what Megger has to offer in the field of power factor testing, that's Delta 4000. So let's start off with the first section of the presentation. Why do we need to test transformer insulation? Before we get into the reasons why, let's talk a little bit about transformer insulation. So the transformer insulation is composed of solid and liquid insulation. The solid insulation is in the form of cellulose. You have paper which is wrapped around the winding, and then you have pressboard barriers between windings, you have pressboard blocks for support. This is essentially made up of cellulose. Cellulose is a naturally occurring polymer, which means it's a chain of thousands of repeating units called monomers. These monomers resemble glucose. As cellulose ages, what happens is this chain ruptures at different points, and this process is called depolymerization. You might be aware of a test called degree of polymerization, DP test, which is done on solid insulation samples in transformer to determine the condition of the insulation. Right? So this is what that test looks at. The liquid insulation is made up of is typically mineral oil. You might find other examples like synthetic esters, natural esters, but mostly mineral oil is used. And mineral oil is made up of hydrocarbons. These hydrocarbons can be different types of compounds. You can have paraffinic compounds, you can have naphthenic compounds, you can have polyaromatic, aromatic compounds as well. And the proportion of these compounds gives the oil its unique characteristic. Oil not only acts as insulation, but it also acts as coolant, which means it helps in the dissipation of heat that is generated when the transformer is put into service. Through the natural process of convection, hot oil rises up, hot oil rises up, cool oil goes down, and oil circulates in the tank, thus helping in the dissipation of heat. This process can also be forced by using pumps, which is the case in some big transformers. A third purpose that it serves is diagnostic in nature. If you need to know about your health, you can get a blood test done, and the blood test results will tell you everything that you need to know about your overall well-being. Just like that, you can. There are several oil tests which are there, and these oil test results tell you about the overall well-being of the transformer. So let's now talk about all the chemical processes that occur in the transformer insulation the moment transformer is put in service. What happens is the cellulose undergoes oxidation. This oxidation process results in the formation of carbon oxides and water. It also undergoes a process called hydrolysis, where it combines with water and degrades. Now, this process is accelerated in the presence of carboxylic acids, which are present in the oil. The oil itself undergoes oxidation, and this process ultimately results in the formation of carbon dioxide and water. But the intermediate processes result in the formation of some byproducts like alcohols, aldehydes, ketones, peroxides, acids. If the acid content becomes too high, then that can result in the formation of sludge. Sludge not only impedes oil flow, but it also attacks cellulose directly, so it's not desirable at all. The different fault processes which occur in oil result in the formation of gases. Hydrogen requires the lowest energy among these gases, and so partial discharge results in the formation of hydrogen. If you have thermal faults, different gases can be generated depending on the severity of the thermal faults. Low temperature faults will result in the formation of methane. If the temperature increases, then that can result in the formation of ethane, and then finally ethylene. If thermal fault degrades into arcing, then arcing would result in the formation of acetylene. You would have seen not all, but most of these gases in your DGA test results. Acetylene is absent. If you see even a little bit of acetylene in your DGA test results, that means that the transformer needs to be taken out of service because it may fail sooner rather than later. These processes that we talked about are influenced by different factors. These factors can be internal or external. External factors include moisture. Moisture ingress can occur through leaked gaskets, oxygen, exposure to oxygen. Solid debris can enter when the transformer is open for maintenance. And then you have internal factors like, again, moisture, which can be produced as a result of some of the processes occurring inside the transformer, and metal particles, which can be generated from the mechanical wear and tear, cellulose particles, which can come off of the solid insulation, and then some of the chemical degradation products that we talked about earlier. So these factors, or the presence of these contaminants, can play a big role in influencing the condition of the insulation. So from what we have discussed so far, we know that insulation plays a big role in the health of the transformer. So to get the maximum life out of a transformer, we need to keep a close eye on the insulation, test it from time to time. There are several oil tests which are done on oil samples, but there are also some electrical tests which are done on the overall insulation of the transformer, and power factor test is one of the oldest. It has been around for over 100 years, and it basically involves measurement of dielectric losses. Recently, the industry has shown a tendency to explore and focus more on variable frequency power factor testing to assess the health of the insulation of a transformer. And we're going to talk about that towards the end of the presentation. So let's start off from the very basic. Let's talk about what is capacitance, what is power factor. Let's try to understand these terms. There are three types of elements. You have resistance, you have inductance, and capacitance. The way these behave when voltage is applied across them is different. When you apply voltage across a resistance, the current that you get out of a resistance is in phase with the voltage, right? An example of a resistance is the conductor. So copper or aluminum, it could be in the form of a cable, it could be in the form of a bus bar, but essentially that's a resistance. Now, if you take a really long cable and make it into a coil, then that becomes an inductance. The inductance, the value of the inductance depends on the nature of its core. If the core is air, then it may have a weak inductance. If the core is made up of high-grade steel, then it will have a high inductance, which is the case with transformer windings. Now, what's exactly inductance? Inductance means that if you apply voltage across a coil, a back EMF will be induced in the coil, which will tend to oppose the applied voltage, and it will oppose the changing current. Because of this, what happens is if you apply voltage across an inductance, the current that you get lags in phase behind the voltage. And for a pure inductance, the lag in phase is exactly 90 degrees. Let's talk about a capacitor. When you have a dielectric which is separated by electrodes, that constitutes a capacitance. What happens is when you apply voltage across a capacitor, the electrons flow not through the dielectric, but they flow to the plates, and the plates get charged. And the way they get charged depends on the direction in which the current is flowing. The extent to which they get charged would be the maximum at the end of each half cycle if you apply an AC voltage across a capacitor. So what happens is, picture it this way: when you have an AC wave, what's happening is current is flowing in alternate direction in every half cycle. So at the end of the positive half cycle, all the electrons have flown in one direction and the plates have been charged to their maximum potential. So the maximum voltage difference that you would see would be at the end of each half cycle. And that's the reason why the peak of the voltage waveform corresponds to the current zero. So because the voltage depends on the current here, the voltage waveform lags in phase behind the current, and the phase difference is 90 degrees for a pure capacitance. Example of a capacitance is insulation. Let's try to understand what do we mean by cosine, because power factor mathematically is cosine of phi. So to understand power factor, we need to know what do we mean by cosine. So let's take a triangle where the angle is phi. Now cosine of phi is going to be the adjacent side of that triangle divided by the hypotenuse. If try to picture reducing the angle to zero. If you reduce the angle to zero, what you do is you end up making the triangle into a horizontal line, which means that the adjacent becomes equal to the hypotenuse, which means that cos of 0 becomes 1. On the other hand, if you increase the angle to 90 degrees, what would happen is you would make the triangle into a vertical line, which means that the adjacent side would be equal to 0, which means that the cosine of 90 degrees would be equal to 0. Now, going by the phase angles that we saw on resistance, inductance, and capacitance, we get we get a power factor of 1 for a resistance and 0 for inductance and capacitance. We can also talk about the impedance here. The impedance is the opposition that's offered to current, and for a resistance, it's just a resistance, whereas for an inductance and a capacitance, the opposition that's offered, the reactance element, depends on the frequency. So the inductive reactance increases with the frequency of the voltage that's being applied, and the capacitive reactance decreases with the frequency of the voltage that's being applied. Let's now try to understand power factor in a non-mathematical way. Power factor can be termed as the percentage of power supply that is used to do work. Take an incandescent bulb, for example. If you supply electrical energy to this bulb, it glows. The filament heats up, emitting heat and light. So the energy that you're supplying to the bulb is getting converted into other forms of energy. And work is being done here. So the filament can be classified as a resistance, and we say that the bulb has unity power factor. Inductors and capacitors, on the other hand, are storage elements, which means that if you supply energy to them, the energy gets stored in the inductor and capacitor. It doesn't get dissipated or it doesn't get converted into heat or light. This energy, if you apply AC voltage across the inductor or a capacitor, bounces back and forth between the source and load, and the direction in which the energy goes depends on is opposite for the inductance and the capacitance, which is the reason why you use capacitor banks for power factor correction. It's because the loads are inductive in nature. So having understood what do we mean by power factor and also what do we mean by capacitance, let's try to look at the theory of power factor testing. So in power factor testing, as I said, what we do is we try to measure the dielectric losses in the insulation. So this test is done on the insulation. What we do is we apply voltage across the insulation and we measure the current that's coming out of the insulation. We not only look at the magnitude of the current, but we also look at the phase angle. Now, ideally, an insulation, we said, is a capacitance, and because of that, ideally the power factor should be equal to 0. The current would lead in phase with respect to the voltage by 90 degrees, but that's not the case because of the presence of contaminants, right? Because of it not being an ideal situation, there is a certain loss component in the insulation, and because of that, we can actually draw the insulation in terms of a parallel RC circuit. Instead of just showing a capacitor, we can say that it has a parallel resistive arm, and the current that flows through the resistive arm depends on the extent of contamination in the oil. So we have a voltage which we apply, we have a current which we measure, and from these two parameters, we calculate the capacitance, the power factor, and the losses using the formula that are shown here. The capacitance is a characteristic of the physical state of the insulation. Capacitance depends on the distance between the electrodes. It depends on the area of the plates. It depends on the nature of the dielectric. Power factor or losses, on the other hand, depend on the quality of the insulation. So we are looking at two different things here in one test. Let's talk about the insulation system inside a transformer. A transformer can be called a complex insulation system, which means that it's made up of multiple insulations. Yes, it's actually more complex than what is shown here on the slide, but for the sake of the test, we can say that the system is made up of three capacitances. The interwinding capacitance, which is the capacitance of the insulation that lies between the high voltage winding and the low voltage winding. And then you have the winding to ground capacitances, which include CHG and CLG, or CH and CL. Now this is for a two-winding transformer. If you take a three-winding transformer, then the number of these capacitance parameters increases. On power transformers, we would also have condenser bushings. Let's talk a little bit about these bushings. So condenser bushings have a capacitance graded design, which means inside a condenser bushing, you have a foil made up of copper in oil impregnated paper, which is wound around the central core, thus creating multiple layers of capacitance. Now, these multiple layers of capacitance can be represented by a single equivalent term called the C1 of the bushing, which is what we measure. And also, there is a C2 term. So here you have a point called the test tap, which is found at the base of the bushing. This test tap is brought out and it's insulated from the core, the central conductor, as well as the ground. And being insulated from the ground, it has some insulation, which can be termed as capacitance C2. So when we run a power factor test on a condenser bushing, we measure both C1 and we can measure both C1 and C2. The reason why this design is used, the reason why condenser bushings are what you see typically in high voltage applications, is because the capacitance graded design results in a better voltage distribution. So with a relatively smaller bushing, you can use it at a relatively higher voltage application. So we have looked at the insulation system for a transformer as well as for a bushing. Let's try to understand measurement modes. So it doesn't matter what power factor test set you're using, these modes you will definitely come across. So let's try to understand what these measurement modes mean. There are three measurement modes. The first one is GST. GST stands for grounded specimen test. What it means is that here, let's say we have a setup where there's a power factor test set connected to a device. I'm not concerned with what's inside the object. It just has two terminals and it has a ground. So I'm connecting the high voltage cable on one end. I'm connecting the measurement lead on the other end, and also there's a ground lead which runs from the object to the power factor test set. Both these leads are connected here by means of two switches. At the moment, these two switches are connected to the ammeter, which is the case in the GST mode. So in the GST mode, the switches are positioned in such a way that both the measurement lead and the ground lead are connected to the ammeter. So whatever current comes out, when I apply a voltage on one end, the current that comes out through the other end as well as through the ground, both of those currents get measured when I operate in the GST mode. So that's the GST mode. And then when you switch to a GST-G mode, what happens is only the ground current gets measured. When you operate in the UST mode, which is under ungrounded specimen test, what happens is only the measurement lead connects to the ammeter, and you end up measuring the current that's flowing out through the measurement lead. So to summarize what we have seen here, we can show it in terms of a table. You have the grounded specimen test with guard. Guard means that the measurement lead gets bypassed, so you end up measuring only the ground current. And then you have ungrounded specimen test. So why do we use these three measurement modes? These three measurement modes enable us to measure currents selectively when we connect to an object. And by doing that, we are able to measure the individual capacitances which make up a complex insulation system. Because when we measure a current, we can calculate the capacitance of the insulation through which that current is flowing, right? So let's get into the process of power factor testing and see how these measurement modes enable us to measure the different capacitances that are present inside a transformer. So we have already talked about what the transformer insulation system looks like. Here you have a two-winding transformer, and there is three capacitances here, CHL, CLG, CHG. What we do is we short the high voltage bushings together, we short the low voltage bushings together separately. The reason why we do this is because we want the entire winding to be at the same potential so that we have a single electrode. And then we connect the high voltage cable on the high side winding and the red cable on the low voltage winding. The red cable is a measurement cable. Typically on your power factor tests, you will see two of these. One will be red in color, one will be blue in color. And one measurement lead is what you would use typically. So with these connections in place, we run the three measurements, one in GST mode, one in GST-G, one in UST. What happens is in the GST mode, the red current and the ground current get measured, and so we end up measuring both CHL and CHG. In the GST-G mode, we measure only the ground current, so we get just CHG. And in third mode, the measurement lead current gets measured, so we get just CHL. So in these three measurements, we have measured the high to ground capacitance and we have measured the interwinding capacitance, but we still need to measure the third capacitance, which is low to ground. So how do we do that? What we do is we swap the leads. So now I have the high voltage cable going to the low voltage winding and the red cable is on the high side winding. Now with the leads swapped, we run those three same measurements again. And this time what we get is on the GST measurement, we get the sum of low to ground and high to low. On the GST-G measurement, we get the low to ground capacitance. And on the UST measurement, we get the high to low capacitance that we measured the last time. So it's a repetition of that same measurement from the other side. And that concludes the overall power factor insulation test. So with that, we have measured the power factor of the insulation of the transformer. Now, if you have condenser bushings on your transformer, you can run a power factor test on those bushings. And the way to do that is to connect your measurement lead on the test tab of the bushing that you want to test on. These test tabs have caps on them, which keep the test tab grounded when the bushing is in service. So you need to unscrew that cap and make a solid connection, solid and safe connection on the test tab. So what you do is you apply voltage up top and you run this measurement in the UST mode. In the UST mode, only the current flowing through the measurement lead gets measured, and so you end up measuring the capacitance between the bushing core or the bushing conductor and the test tab, which is the C1 capacitance. To measure the C2 capacitance, what you do is you swap the leads again. So this time the high voltage cable is connected to the test tab and the red cable is connected up top. But this time you change the test mode to GST-G. With the GST-G mode, you only measure the ground current, and so you ignore the current that flows through the C1 of the bushing, and you only measure the current that flows through the C2 of the bushing. And that's how you measure the C2 of that bushing. Let's look at some typical test results now. These are the overall test results. Here you can see that it basically shows you 7 rows. Rows 1 to 3 show you the measurements done on the high side. Rows 5 to 7 show you the measurements done on the low side. The row number 4 is just a mathematical validation of the test results. What you have here is the test voltage. You can see that the test voltages are different for the high side and the low side, and the reason is because the test voltage needs to be appropriate. You cannot, typically it's done at 10 kV, but you cannot exceed the voltage rating of the winding that you're testing on. So if I'm testing on a low voltage winding which is rated for 1 kV, I won't exceed 1 kV, which I believe was the case here. And that's the reason why the low side winding was tested at 1 kV instead of 10 kV. So typically the test is done at 10 kV, but if the rated voltage of the winding that you're testing on is less than 10 kV, then you want to reduce the test voltage and apply a voltage which is close to but not greater than the rated voltage of the winding. The capacitance values that you get are in nanofarads typically for the overall test, and the power factor values are expressed in percentage. I have seen some people question and say that why are we getting power factors greater than unity? Power factor is not supposed to be greater than unity. That's true, power factor can't be greater than unity. What we are seeing here is percentages, right? So when I say 0.34%, the absolute value is 0.0034. So these values are actually very close to zero. These are really small numbers, and for convenience, we express them in terms of percentage. You will see power factor, you will see temperature corrected values for power factor, and we'll talk a little bit about temperature correction of the power factor values towards the end. You will see the current that the insulation drew. You will see the losses associated with it, and the losses and the power factor are related to each other. Then there's a column that says VDF, and VDF is stands for voltage dependence factor. We'll talk a little bit about that towards the end as well. IR stands for insulation rating, not insulation resistance. Insulation rating is basically the software grading your insulation on the basis of where the power factor values stand with respect to the limits that are provided on the software. Let's move on to the bushing power factor test results. On bushing power factor test results, you want to compare your field test values with the nameplate values. The nameplate values, the nameplate is at the base of the bushing and typically has values for C1. Both capacitance and power factor values are provided. If you're lucky, you may even see nameplate values for C2 on the nameplate. You will compare your field test values with the nameplate, and you don't want to see too much of a change between the measured values and the nameplate values for C1. On C2, however, you can see field test values which would differ from the nameplate values. The reason being that on the values that are punched on the nameplate are from the bushing manufacturer, and the manufacturers and these bushings are tested while being mounted on a stand. When the bushing is mounted on a transformer, the setup changes, and that results in a different value of C2. That doesn't mean that there is anything wrong with the bushing. In a case like that, the first time you run the test on the C2 of the bushing would become your reference, and henceforth any subsequent tests that are done on that C2, you would compare those values with the first value that you got when the bushing was tested while it was mounted on a transformer. You can also see here that the test voltage is much lower. It's at 0.5 kV for C2. The C2 insulation is not rated for a high voltage, so typically these tests are done at 0.5 kV or 1 kV. So you get your test results. Now, what do you make of them? How do you validate those test results? There are several guidelines. What we follow here is the IEEE guide, the field testing guide, which is C57.152, and it has some information. It has some limits for power factors on new transformers, for power factors on service age transformers, and also it talks about changes in capacitance. Capacitance, if you remember, I said it depends on it tells you about the physical state of the insulation. So if there is a change in the capacitance, it means that there has been some physical movement inside the transformer which has caused the capacitance to change. If that capacitance change is drastic, then the cause needs to be investigated. The transformer may need to be taken out of service. So keep an eye on not just the power factor, but also the capacitance value that you get. For capacitance, there is no set limit. It's a design parameter. So the value that you get the first time or the value that you see on the factory test report is the reference value. And that's what it needs to be compared against. For bushings, for C1 measurement on bushings, what the field testing guide says is if the power factor increases by 1.5 to 2 times the initial reading, then the bushing needs to be tested more frequently, and you need to keep a close eye on the bushing. If the power factor exceeds thrice the initial reading, then the bushing needs to be taken out of service. Also, the capacitance needs to be monitored. If there is an increase in capacitance of more than 5%, then that's cause to investigate. Why would the capacitance increase? On a condenser bushing, remember I said it has a capacitance graded design, which means it has multiple capacitances connected in series. Now, if there is damage inside the bushing resulting in shorting of some of those layers, then you end up shorting some of the capacitors, and that increases the overall equivalent capacitance C1. So the C1 will tend to go up if the layers get shorted. So that was power factor testing. Let's now talk a little bit about about variable frequency power factor testing. Before we get into that, let's try to understand what goes on when a dielectric is subjected to an electric field. When you apply voltage across an insulation, two types of losses occur. Conductive losses occur because of the true conduction element in the insulation, because of electrons actually moving through the dielectric. Polarization losses, on the other hand, occur because of the different polarization processes which occur in the insulation. These polarization processes are of different types. You can have electronic polarization, which is the quickest, and you can see in the figure how the electrons respond to the electric field. In molecular polarization, the ionic bond within molecules get deformed, and in orientational polarization, you have whole molecules aligning in the direction of the field. In solids, you can have interfacial polarization occur at electrodes and crystallite interfaces. In systems with two or more dielectrics, as is the case with transformer, you can also have space charge polarization. So these different polarization processes depend on the frequency of the electric field. When we talk about frequency, we are talking about how frequently the electric field polarity changes. Right? So as the frequency increases, the frequency with which the polarity changes also increases. So you can have higher losses occurring, and also some processes may not be able to keep up with the frequency of the field. For example, orientational polarization, if you continue to increase the frequency of the electric field and you continue increasing it and you increase it to a high number, the orientational process may not be able to keep up with it, whereas electronic polarization, which doesn't require much effort, which takes place relatively quickly, would still be able to keep up with it and will continue happening. So the polarization processes and the losses associated with them differ with the frequency of the electric field that's being applied. Another thing that we can talk about is the different currents that occur when a unidirectional electric field is applied to it. So when we talk about a unidirectional field, we are talking about each half cycle of the voltage of an alternating voltage, or we could be talking about DC. What happens is when the insulation is subjected to an electric field, initially draws a certain amount of charging current, which depends on the capacitance and which drops fairly quickly. You also have an existent absorption current, which drops relatively slowly, and that current is because of the orientational polarization. You also have a conduction current, which is the true conduction element, and it stays constant, doesn't change with time. So as the electric field is kept on for a longer duration, you have the other currents dropping, whereas you have the conduction current staying positive, is staying constant. And so eventually, as time progresses, the conduction current becomes more dominant. As we decrease the frequency of the voltage that we are applying across the insulation, it starts to resemble DC more closely, and so we get higher conduction losses, or the conduction current dominates in the lower frequencies. So the variable frequency power factor testing exploits these concepts, and it uses these concepts to determine the state of the insulation. It gives us information to where we can detect changes happening in the insulation before a traditional power factor test can. So let's talk about a typical DFR measurement. A narrowband version of the DFR is carried out by us between 1 Hertz to 500 Hertz. And at different points, power factor values are measured. By joining those data points, we get a DFR curve. Now, this is what a typical curve looks like. It's more or less horizontal with a little bit of a dip in the middle frequencies. And it has a tip up in the lower frequencies, which depends on the state of the insulation. Just to show you the kind of information you get from a DFR measurement, here I have 3 DFR curves from 3 different transformers. If you look at the 60 Hertz values of those transformers, all 3 of them are pretty good. 0.28, 0.24, 0.16. They are well within the limit of 0.5%. But you can see that in the frequency range of 1 Hertz to 15 Hertz, you can see that the curves differ from each other a lot in the lower frequencies. Not saying that one transformer is bad and the other transformer is good, but there can be changes depending on the state of the insulation in the lower frequencies. The best way to go about it is to trend the DFR curves over time, but you also have to keep in mind that temperature does play a role in the DFR measurements, which is the reason why I've mentioned the temperatures here. The DFR curve, even though it retains its shape as long as the insulation stays the same, the curve tends to shift horizontally with temperature. So as the temperature increases, the curve tends to shift to the right. So the ideal way of trending DFR measurements is to try to take measurements at the same temperature so that you can eliminate the influence of temperature on the measurements, and you can get proper curves which can be superimposed on each other, and you can see the extent of the tip up in the lower frequencies. These are some typical test results that you can get on bushings. You get either more or less of a horizontal curve, or what you get is this curve with an upward slope. Here you can see the nameplate values and the measured values, and you can see that there isn't much difference between the measured and the nameplate values, even though these bushings are over, I would say 25 years old, 25 years old. If you go to look for limits on variable frequency power factor testing, it's still a relatively new topic compared to traditional power factor, which has been around for 100 years. You won't see too many limits. One set of limits that I have is for you here is from the Seagray technical brochure 445, which deals with maintenance and testing on transformers. It has some limits provided at different frequency points. But you can see that it says that these limits are indicative. Now, if you look at the values that I have here, the nameplate values themselves exceed the 60 Hertz values that are expressed in the table over here. So these are just reference points that you could use in case you want to refer to them. DFR or narrowband DFR has a lot of value, especially when it comes to detecting deterioration in bushings. This case here highlights how DFR and how narrowband DFR works. Now, this is the case of a transformer which was tested, and we saw different stages of deterioration in the bushings. So here you have no deterioration, pretty much, even though this transformer was old as well. I believe these bushings were around 20 years old. Here you cannot see any change in the power factor on the high voltage bushings, but on the X1 bushing, you can see that the power factor is starting to increase. It's not alarming, however, it's just a little bit of an increase. But in the X2, X3, XO bushings, you can see that there's clearly a huge increase in the power factor. Now, these are, if you compare them with the nameplate values, yes, you can clearly make out the extent of the increase in power factors. But what if the nameplate was corroded? What if you didn't have that information? If you were to just look at the values themselves of individual bushings, they wouldn't still look bad. Well, the X2, X3, XO bushings do look bad, but X1, for example, you would say nothing about it. Now let's look at how DFR measurements compare those three bushings, those 7 bushings. So you have the what I call the good, which is the high voltage bushings, and you can see that the curves are more or less horizontal here, and the scale here is massive. So they look as if they're pretty much on the x-axis, but that's not the case. But the shape of the curve is that it's pretty much horizontal, and there's no tip up in the lower frequencies. And then you have the X1 bushing, which is the bad, where the power factor is starting to climb up. You can see that the change is pretty evident in the lower frequencies here. As you go down below 10 Hertz, you can see that it's easily differentiable from the other bushings. And then we have the ugly, which is these 3 bushings where the power factors have gone up all the way to 10%. So here you actually have two curves for two curves instead of one. They pretty much follow the same path and they go all the way up to 10%. And then you have the third bushing here, which goes up to 8%. So you can see here that the difference is pretty evident when you look at the frequency range 1 Hertz to 15 Hertz, which is why we stress on the importance of going down all the way to 1 Hertz to look at the power frequency when we perform variable frequency power factor testing. Let's look at another example which kind of shows you the readings that you get on bushings that are mounted on stands here. This isn't bushings mounted on a transformer. You can see bushing A, there isn't much difference in the measured values on the nameplate. You can see what the DFR curve looks like for that bushing. And on bushing B, you can see there's a little bit of an increase in the power factor, and you can see how the shape changes. There's a tip up in the lower frequencies. Let's now talk about some best practice pointers in order for us to be able to do this test in a safe manner and also get accurate results. So the bushings need to be shorted from point to point, and sufficient clearance needs to be maintained. This test is typically done at 10 kV, which is a high voltage, and you want to make sure that you are well aware of what's going on, you clear the area, you maintain your distances, and maintain safe distance. Safety is really important when it comes to doing this test. And then you also need to consider, for accuracy, you need to consider the external factors like temperature and humidity. We're going to talk about the temperature correction, but as far as humidity goes, you want to try avoiding in humid conditions. What happens is there is condensation on the surface of the bushings, and that gives rise to surface leakage currents, which are currents which flow along the external surface of the bushings from the conductor to the tank. The instrument measures these currents from the ground lead, and it's unable to differentiate between the surface leakage currents and the current which is actually flowing through the insulation. So you end up getting a higher power factor value than what you should be getting. That's why it's essential to test in dry environments, avoid testing in humid conditions. I myself have been in a situation where early in the morning we tried testing and we got really high values, and then 2 hours later when the sun was out, we tested the same transformer and the power factor came down by actually close to 70%. Avoid testing in freezing conditions. Ice and water have different electrical characteristics. So if you test at sub-zero temperatures, the moisture in the oil freezes over, and that will give you a different power factor value than what you would get if you were testing at, let's say, 20 Celsius. Isolate the transformer completely. I've seen a lot of people test a transformer with other components connected, like surge arresters or insulators in parallel. When you have those components connected, you're not just testing the transformer, but you're also testing those components. And those components can have a higher power factor value than the transformer. The instrument would again not be able to differentiate between the resistive current coming from the parallel components and the currents coming from the transformer, and so it will most likely give you a higher power factor value than what you would get if you were to just test on the transformer. So for accuracy, it's very important that you test with the transformer isolated from everything else. Let's come to the final section of the presentation where we talk about the instrument and some of the features that it provides. So the Delta 4000 has the following features and benefits. It can be used to do power factor test and narrowband dielectric frequency response. It can also measure excitation current, can be used to do high voltage turns ratio with the help of a capacitor as an accessory. Can be used to do a tip-up test, which is where you run a power factor test at different voltage levels and see how the power factor changes with voltage. This test itself is not limited to just transformers. It's an insulation-based test, and many assets have insulation on them, and so power factor testing can be done on those assets. So it has a wide variety of, can be used in a wide variety of applications. Specifications, it has up to 12 kV. It's capable of putting out up to 12 kV, and frequency range, what we provide is 1 Hertz to 505 Hertz. And I've already stressed to you the importance of going down all the way to 1 Hertz, even while doing narrowband DFR testing. As far as the output current goes, it's capable of handling 300 milliamps. The current that you get, or the current that the instrument measures, depends on, of course, the capacitance of the insulation that's being tested. It has a two-piece design. It is easily portable, makes it easy to use in rugged environments. It generates its own signal, which means if you're testing in environments with really bad input voltages, the condition of that input voltage won't affect the output that's coming out of the test set, and it won't affect your test results. It has high signal to noise ratio, which enables it to be used in really noisy environments like high voltage substations. Software-wise, the software that's used is called Delta Control. Delta Control is the primary software, and it can also be used with PowerDB. PowerDB is the software that is used with most of our instruments, and PowerDB provides you a comprehensive test report instead of just values on a CSV sheet. So what you get is a proper test report, and you can maintain a proper record. Also, if you have other Megger instruments like our TTR test sets or our winding resistance test sets, those would generate reports in PowerDB as well, so you can have multiple test reports for the same asset in the same format. PowerDB has a pro version, which is the licensed version with which you can maintain a database of test results on various assets done in various locations, and that's a paid version of the software. We also have a free version called the light version, with which you can still store multiple tests on a single file. So if you have you can have one file dedicated to one asset, and on that file you can store multiple tests as you go on doing multiple power factor tests on it over time. You can save all those tests on that single file, so that helps you keep a record of the previous tests and help you keep track of the results of the values in a better way. Let's talk about individual temperature correction now. So this is one of the most important features, or perhaps the most important feature, which differentiates our power factor test set from the other test sets that are around. Power factor, as I mentioned, is temperature dependent. At different temperatures, you would get different power factors. And if you want to trend power factor values over time, then it's important that you normalize the power factor value to 20 Celsius. Earlier, there used to be in the guides, there used to be a table that had some generic temperature correction factors, and it was basically it was accompanied by a statement which basically said that these factors are generic and they may not always work. And that was the case more so if there's moisture in the insulation of the transformer. What we found is that the thermal response and the frequency response of an insulation are related. They're related by this equation that's shown here called the Arrhenius Equation, and we exploited this equation to come up with a way of correcting a power factor for temperature. So the way it is done is you run a DFR measurement on the intertwining insulation, on the CHL insulation, and that DFR curve that you get, as I mentioned earlier, it shifts with a change in temperature, right? So let's say you run a DFR measurement at 30 Celsius. Using the Arrhenius equation, it's possible to determine by how much the curve would shift horizontally to compensate for the change in temperature. So if I want to find out where the curve would be at 20 Celsius, I can do that by using the equation, and then I can determine what point on the DFR curve would correspond to 60 Hertz. So that's how I end up determining from a DFR measurement at 30 Celsius what the 60 Hertz power factor would be at 20 Celsius. And this method is pretty accurate. We can provide you with additional information, and it's a pretty valid method which you can use. At this point, there is no other method available for temperature correction of power factor. Voltage dependence detection is another feature which our power factor test set has, which is unique to our test set. when you do power factor testing on rotating machinery, you would see a tip up in the power factor, which means that the power factor increases with voltage. But that shouldn't be the case when it comes to transformer insulation. Transformer insulation power factor should not increase with voltage. If it increases with voltage, it means that there is additional ionization, additional losses occurring in the insulation, which is causing the power factor value to go up. What our power factor test set does is it does a harmonics analysis of the current to determine whether the power factor is voltage dependent or not. So it gives you a parameter called the voltage dependence factor, VDF, and based on the value of that VDF, you can decide either to do a tip-up test or not. By doing a tip-up test, you actually verify whether the insulation is voltage dependent or not. So your typical values will be between 0.01 to 0.09. If you get a higher value, then basically the software is suggesting to you that the insulation might be, the power factor might be voltage dependent, and then you can go ahead and do a tip-up test to verify whether that's actually the case. So here I have two cases that shows you how this works. You get a high number of VDF. Let's say in this case, the VDF was 0.174. We proceeded to do a tip-up test, and we did see the power factor climb up with increase in voltage. So in this case, yes, that the power factor was actually voltage dependent. In another case, the VDF was 0.173. We again proceeded to do a tip-up test, but in this case, it turned out that the power factor was not voltage dependent. There are other accessories. There are accessories available with the power factor test set. I'm not going to talk a whole lot about it. I'll just briefly go over some of these. The accessories include some shorting cables for shorting the bushings. You have different bushing adapters which allow you to make a solid connection on the test tap. And then there are semi-conductive straps which can be used for hot collar tests. We also provide a cart as an optional accessory in situations where you don't need to pack the power factor test set up and put it in the back of a pickup truck. If you can afford to keep it as it is, you can use a cart to provide some level of portability to it. So for example, if you're a transformer manufacturer, you can just have it on the cart and then move it around the plant. We have made some design changes to the leads. What we have here is the high voltage clamp, for example. It has an adjustable jaw on it. It has a hinge. The hinge takes some pressure off of the clamp, so now the clamp doesn't get disconnected from the bushing under the weight of the cable. Also, the termination has a banana plug on it. So with that, you can connect this little connector, and with this connector, you can make a safe and solid connection on the test tap of the bushing. To make sure that this doesn't slip from the test tap under the weight of the cable, we also provide a string which you can run around the petticoat of the bushing, and that supports the cable. Besides the Delta 4000, we also have the TRAX, which is a multifunction test set. It's capable of doing several tests, and one of those tests is power factor test. All the features that the Delta 4000 has, the TRAX has as well, or rather the TDX plus TRAX combo has as well. So TDX is the high voltage unit which actually puts out the voltage, and TRAX is the control unit or the brain of the instrument. So that's all I had. If you have any questions, if you haven't already typed those in the chat, you can email me directly. That's my email address. Over to you, Mike.
All right, thanks. So as stated before, the presentation portion of our first segment has officially concluded. We now have a few minutes to answer as many of your questions as possible. If you do have any questions, please submit them now into the Q&A box on the right side of your screen. As a reminder, we do have one more segment after this Q&A session, so please stay tuned. Our first question is going to go to Ken. Ken, could these tests add further damage to the transformer insulation?
Thank you, Michael. Thank you, Sanket, for the great presentation, and thank you all for attending here today. Concerning the test further damaging the transformer insulation, no. Typically, this test will not damage the insulation unless you are applying a voltage that is higher than what the windings are rated for. You always want to look at the transformer nameplate, and if you enter the transformer nameplate voltages into PowerDB, we actually calculate what the test voltage should be to prevent you from damaging the transformer. But on larger power distribution transformers, if you're applying 10 kV and the winding is rated for 160 kV or higher, no, you're not going to damage that transformer winding.
Thanks, Ken. Dinesh, our next question is for you. Degradation of PF or capacitance values. Does it differ in different types of transformers?
Good afternoon, everyone. And this question is what I would call as we can talk on this question for an hour, but just to give you some idea on this thing, whenever you talk about degradation of power factor or capacitance value, you are talking about values increasing. Typically the values would increase, and that would be an indication of insulation being deteriorated or aging. Now, that can happen for a number of reasons, and the question is asking, is it going to be different for different type of transformer? Not only it's going to be different for different types of transformer, but also if the two transformers were designed the same way, based upon how they are being used, what kind of loading has been put on the transformer, what kind of faults they have seen, the condition of oil inside the transformer, all those kind of factors would impact your power factor measurement. So power factor is testing, or capacitance value is an indication of the condition of the insulation and how you operate and how you treat your transformer. That is going to be a big factor that would define the power factor values staying stable or increasing over a period of time. In addition to that, trending is a very important factor. When a transformer is being manufactured, typically factory would provide the baseline values or the reference values, and it is very important to compare your numbers with those reference measurement. So to kind of give a quick answer to this very in-depth question, yes, the values would differ for different kind of transformer, the insulation used in it, and the way transformer is being utilized.
Thank you, Dinesh. Ken, do we need to remove the bushing separately from the transformer to measure the C1 and C2?
Thank you for the question. You do not need to remove the bushing from the transformer to measure C1 and C2. You will, however, need to remove that bushing tap that Sanket showed in one of the connection hookups for the Delta 4000. I do want to mention, however, that some recent studies or reports that I've seen show that you may have different measurements when you measure the bushing separate from the transformer and then when it's installed. And it's not necessarily an indication that there is a problem with the bushing. It's just that I think it's the grounded specimen test that may differ when it's connected to the transformer itself or if it's standalone. So again, no, you don't need to remove it to test C1 or C2, but you may experience some slight measurement differences if you do measure it in the transformer installed and then separately.
Thank you. Dinesh, how do you measure capacitance of bushings that do not have test taps?
This question is kind of on the similar line as the previous question. You can broadly classify bushings into condenser type and non-condenser type. And when you're talking about, like 30 kV or below, you typically run into non-condenser type bushings. And for those, it is very typical to not have a capacitance tap or the test tap. And in those cases, you are not trying to measure the capacitance value. You're trying to see if you can perform tests like hot collar test, which would give you the milliamps and watts. And then you use those values to check the condition of the bushings. When it comes to the non-condenser type bushing, if the bushing has not been installed as yet, then you may want to perform a GST test, which would be from the center conductor to the flange of the bushing. But once the bushing has been mounted inside a transformer or on a breaker, then you don't want to perform that test, because as Ken mentioned, that the readings would be different and it won't provide much meaningful information. So if the bushing is already in service on a transformer or breaker, then your best bet would be to perform a hot collar test on those bushing that doesn't have the capacitance tap. And Sanket did show some of the accessories, and one of the accessory was the hot collar straps, and those are semi-conductive straps, and depending upon the size of the bushing, you may perform 1, 2, or even as high as up to like 5 hot collar tests at different levels of the bushing under the petticoats that Sanket mentioned. So again, to summarize, you would run a hot collar test on non-condenser type bushings in case you don't have the test step or the capacitance step.
All right, thank you, Dinesh. Sanket, how important is it to perform power factor tests on dry type transformers?
So power factor testing on dry type transformers, the value that it provides is a matter of opinion. It's not my statement. It's what the IEEE test code for dry type transformers says. So it does mention power factor testing, and it says that the voltage would be 1 kV pretty much. And what it says is that you cannot apply the same limits that you can for an oil filled transformer. And think about it. If you think about it, on a dry type transformer, it's open, right? When you measure a capacitance, we are looking at the dielectric between two electrodes. When you measure on a transformer in which the active part is basically exposed to the air, you cannot get reliable values. But still, I mean, the way, if you do want to proceed and do power factor testing on dry type transformers, the way you want to go about it is trend the values and see how they are changing over time. Of course, external factors will influence the power factor values more easily with the insulation being exposed. But that's the only way to go about it. There are no specified limits. For example, for oil immersed transformers, you have a limit of 1% or a 0.5%. There are no such limits provided for dry type transformers. And for this reason, I mean, depending on the insulation type that is used, there are different types of insulation that are used in dry type transformers, and the power factor value can be influenced from that as well as the external environment. So the key is to compare the values and see how they have changed over time, and hope that the external environment isn't playing too much of a role in how the values are changing.
All right, thank you. Dinesh, what can cause PF and capacitance to decrease?
So when we talk about power factor or the capacitance value going down, I will cover the power factor values first. When you talk about power factor values going down, I want to highlight this thing, that insulation cannot improve by itself unless you do some, like oil processing or something like that. Then yes, power factor values would improve. But if you have not done any of those kind of things, then power factor value cannot improve by itself, because insulation cannot improve by itself. So anytime you run into values that have either improved, or we have seen cases where you run into negative power factor, and we all know that the best power factor you can hope for is 0. So anytime you run into those kind of cases, it's an indication that there is something not right, and that something not right could be a user error, or most of the time what we have seen is that there is a grounding issue, or there is a surface leakage happening on the surface of the bushing, and that could be because of the condensation on the bushing, dirt, or high humidity environment that can certainly affect the surface leakage current, And what the surface leakage current basically does is that it increases the phase angle between voltage and current, and whenever there is a higher angle between voltage and current, the cosine of that angle goes down, and it seems like the power factor has improved. We have written papers on this thing, and if anyone is interested, they can reach out to Sanket, and we would be happy to share the paper that goes in depth into talking about what to do when the power factor suddenly starts to improve for no apparent reason, or when you get negative power factor values, what you should be doing.
Thank you, Dinesh. Sanket, what about PF measurement in the case of 3-winding transformers?
So a 3-winding transformer, as I mentioned earlier, it would introduce some additional elements. So for example, on a 2-winding transformer, you have C high to low. Now, if you consider a 3-winding transformer, let's say with 1 primary and 2 secondaries, you would have additional interwinding capacitance in the form of CHL1, which is high to low 1, and then you have C high to low 2. You would also have interwinding capacitance between the first secondary and the second secondary. So you have introduced, now there is additional capacitances which come into play, and the power factor test set would again use those 3 measurement modes to differentiate between one capacitance and the other, and you would still be able to measure all of those capacitances by using the right mode. To talk about our power factor test set, the software itself, the PowerDB software, has a test form dedicated for 3-winding transformers. So all you will do is just pull up that form and just click on the measurement boxes, and the form has the measurement modes already pre-selected, and it shows you what all capacitances are being measured, as it does for a 2-winding transformer.
All right, thank you. Ken, what is the normal capacity output current for the Delta 4000?
So the Delta 4000 is capable of 100 milliamps continuous output. It can do 200 milliamps for 30 minutes and go up to 300 milliamps for 4 minutes. If you are measuring large capacitance specimens like cables or generators and motors, these will draw more current, and you can use what's called a resonating inductor to cancel out the extra capacitance and allow for testing.
Thanks, Ken. Sanket, if you are doing the VDF test, is it still necessary to do the regular power factor test?
Yes, so VDF is a factor which is provided to you by the software when you do a regular power factor test. So let's say I was testing a transformer and I ran a regular power factor test. That's when I'll get the VDF right there, and then based on that value, if I see a high value of VDF, the next step would be to do a tip-up test. So VDF is not a separate test in itself. VDF is a parameter which the software provides to you when you do a regular power factor. And based on that value of VDF, then you can decide whether you want to do a tip-up test or not.
All right, thank you. So, Ken, how can you correct the power factor for temperature if I don't have a Delta 4000 or the tracks? Can you suggest an alternative way?
Sure. So the way that has been used for many, many years would be to look at what's called a temperature correction table. A temperature correction table is based off of, let's say, a transformer year, what kind of insulating liquid, what the rating is on the winding. These will get you in the general ballpark for a temperature correction value that you can use if you don't have the Delta 4000 or the tracks. As mentioned during the presentation, the way that you calculate the ITC is by using the Arrhenius Equation. So for those of you who are intrepid out there, you can always cut your teeth on some of that that chemistry and that big equation there. So yes, there are multiple ways that you can go about getting a correction factor. And what people have typically used in the past is that temperature correction table.
All right, thank you. Dinesh, what is considered high humidity? 50% or above?
Okay, I will certainly answer that, but I want to add one more comment to the previous question on how do you correct for temperature, the power factor readings for temperature. So as Ken rightly mentioned, that you can use temperature correction tables if you don't have the option of running a individual temperature correction method. I do want to, however, point out this thing that when we talk about the temperature correction tables, those are purely based upon the nameplate data. If a transformer that's 50 years old or a transformer that's brand new installed yesterday, they would use same correction factors. And we know that insulation deteriorates or ages with loading and many other criteria. So using those temperature correction table, as Ken rightly mentioned, that it would put you in the ballpark area, but there are some inherent deficiencies in those temperature correction tables because those are generic temperature correction tables, and as I said, like, it is purely based upon the nameplate information of a given transformer. It does not distinguish based upon the loading, the things that the transformer has gone through in its life cycle, any kind of change in the oil or any kind of fault it has seen, what kind of temperature variations it has seen. It does not take into account any of those things. So just wanted to add that. I will now come back to the question on the humidity. So the question is, what is considered to be high humidity, 50% or above? Typically, it is considered that whenever you have a humidity more than 50%, you should try to avoid doing the testing. I do realize that there are parts in the world where humidity is always going to be in more than 50%. In those cases, you are limited with what you have available. But as I mentioned, that anytime the humidity is more than 50%, it can impact your measurement. And the other aspect is that, like temperature, there is no correction factor for humidity. So if you have a high humidity, it can lead to the condensation on the surface of the bushings that can lead to tracking, and that can affect your power factor measurement. So yes, you can perform the test, but because there is no correction for that, your results might be skewed and may not be a true representation of the condition of the insulation.
All right, thank you, Dinesh. It looks like that's all the time we have for this Q&A session. We apologize if we didn't get to your question today, but we will follow up with you offline in the following weeks. With this, we'll begin our second presentation of our BPS. Our second presenter today is Dr. Diego Robolino. Dr. Diego Robolino is our Business Development Director. Also, to assist with the question and answer session, we will have our two panelists still with us, Ken Petrov and Dinesh Chajer. All right, looks like we're all ready to go. Let's go ahead and get started. Thank you for joining us today, Dr. Robolino.
Good afternoon, Michael. Good afternoon, everybody. It's always a pleasure to be participating on these webinars and sharing some information, some interesting information, hopefully with you. Hope everybody is doing well. And let's talk a little bit more about insulation, because Sanket already did a very good introduction into the fundamentals of AC excitation of insulation and what is the process basically, and the importance basically of power factor in the insulation assessment, especially focus on transformers. But as he mentioned before, power factor is not only power transformers, it is instrument transformers, cable, motors, any kind of insulation, liquid insulation, solid insulation. A power factor piece of equipment can help you analyze those results and provide some condition assessment. Okay, with that being said, let me introduce a little bit of the topic right now. We're going to talk about dielectric frequency response. What we were talking originally in the initial presentation was power factor and narrow band dielectric frequency response, and I want to be clear about the difference between narrow band and dielectric frequency response, because when you talk about narrow band, That is part of the power factor test set. And that is a test that you run between this 1 hertz and 500 hertz. That's the reason why we call it narrow band, right? And it's providing you information about the condition of the system. On the other hand, we have dielectric frequency response, which is the full spectrum of the insulation, looking into a frequency band between 1000 hertz and 1 millihertz typically. So why are we performing this AC insulation test? And I just want to emphasize a little bit on what Sanket mentioned already. This is one of the most important tests that you can do on high voltage electrical systems. You are looking into the possibility of any failure condition that could happen. You are looking into the reliability of the system by looking into the life of the equipment, which is based on the life of the insulation of that equipment. And in other words, you can be also, I would say, proactive in your decisions because you can determine issues before permanent management can go over. So this prevents also some accelerated aging of the system. The way that you do this, power factor by itself is just a point of information. And here I want to make some more differentiation, not just focused on what the value of power factor is. But when we look at power factor per se, we're looking at line frequency power factor. So that is basically, if you look into this graph that I have right now on my screen, when we talk about line frequency power factor, you're looking only at the value of your power factor at 60 hertz or 50 hertz. When we look into narrow band, now you have this spectrum. So now you're going between 1 hertz and 500 hertz. All this spectrum of information is now given to you. So you have the ability to determine much more based on the information that you get from all these frequencies, from all these dielectric response. But when you talk about dielectric frequency response, it's all this information that you're available now to do the analysis. And it makes a big difference, a big difference. If we look into this, right, we need to go step by step. One of the things that Sanket mentioned before is power factor depends on the type of electric field being applied, on the temperature. Temperature is one of the biggest factors. And that's the reason why, if we want to compare previous tests, we need to normalize those to 20 degrees C. So when we talk about the confidence at 20 degrees C of line frequency power factor, right? That is the traditional test. You go, you run your test, you do your power factor test at line frequency, you obtain a value. You need to normalize to 20 degrees C. Very good questions after the first part of the webinar, talking about how to normalize this. I think I have another idea. When somebody was asking, if I don't have the delta and I don't have the tracks, what is an alternative solution? The alternative solution for me would be to have an Idax, and I can look at the full spectrum and go from frequency domain into the temperature domain. But power factor by itself tells me very little. What is better than that, of course, if I look into the limit set by the standard, if you have no historical data, the only thing that you can look at is the limits, you know, that you can find in IEEE or IEC standards. But then what is good is to do trending with line frequency power factor. That is the best approach that you have with line frequency power factor. Now you're looking, and I think that Dinesh already mentioned before, your manufacturing data from your FAT or your factory acceptance test, your commissioning test, and whatever testing was performed during the service life of that transformer or any other piece of equipment. But now you're looking into how this is changing. And if you are able to properly correct to 20 degrees C, then you're going to see very interesting things. The problem that we have seen is if the insulation is changing, of course, you may not see, right, the influence of temperature if you do not correct that properly. And that's the reason of individual temperature correction. What is better than that? Of course, to look into the narrow band DFR between 1 and 500 hertz. With that information, now we're not focused only on the 60 hertz. Now we have a wider spectrum to analyze, right? And we can look at the changes within that frequency, not only to do the individual temperature correction, but also to see how the response continue to be active in the system. Is there any deformation? Is there any non-typical response? How this insulation has changed? You know, sometimes people will say, well, I would expect to have a higher power factor at higher temperatures. And maybe the dielectric response will tell him that that is not the truth for that specific type of insulation. So things will change. You have aging processes. You may have a fault in the system that will change the condition of the insulation. There are many things that will happen during the service life of the equipment. So going from the traditional power factor to do some trending, to do the narrowband, and finally to do some definitive analysis of the insulation using DFR. This is the full spectrum dielectric frequency response, going from 1 millihertz all the way up to 1000 hertz. Here you can have a conclusive assessment of the solid insulation and the liquid insulation independently, and we're gonna look into this separately. So just to get into the theory of DFR, basically DFR is an advanced application of power factor testing. Okay, we do the same analysis. We're changing the frequencies. When we change the frequencies, of course, frequency is inversely proportional to time. So if I go into high frequencies, it's a very fast test. If I go into very low frequencies, it's a slow test, right? So we apply up to, under normal conditions, normally we apply a low voltage, and the low voltage is 200 volt peak or 140 volts RMS. And this is another difference, because especially for oil impregnated paper, we have seen, and it makes sense in oil paper insulation systems, that the power factor under ideal conditions, you will get the same power factor value. The idea of applying 10 kV most of the time is to overcome the influence of noise in the substation. But otherwise, because we're talking about a high capacitance on your transformer, 200 volt is sufficient to get a very nice response and to measure the power factor value, unless a voltage dependence is detected in the insulation, and that's something that was highlighted on the previous presentation. Anyhow, getting into some simple equations here, when we're talking about polarization current, and this polarization process that Sanket already mentioned, getting into the effect of the AC and the molecules that we have internally in our insulation system, this polarization process will create what we call the current density. And this current density is directly related to the polarization process and the alternating excitation signal. This electric field can be expressed, right, together with the polarization as current density. And from here, we see that one of the parameters that pops up is the susceptibility of the material as a function of frequency. So when we look into the function of frequency of this current density as a polarization process, we will identify now two components. On this side, you can see that we are looking into the capacitive component of the complex permittivity of the system. And this is basically what we look, and it's directly correlated to the capacitive real component. When we look into the right-hand side here of the complex permittivity, now you see that this corresponds to the resistive component. And this will be basically in phase with the excitation field. And this is the part that corresponds to DC conduction and relaxation losses, and what is called, and we also know it as the loss component or the loss factor in the complex permittivity system. With that being said, we can determine then, just bringing those numbers into terms of complex permittivity, you will have a real component of the complex permittivity and an imaginary component of the complex permittivity. And from here, one of the things that we need to be clear is that this dielectric frequency response is basically a signature of the dielectric system as it is. This is something sometimes people say, do I have to do trending on the dielectric response? No, because this is a picture of today, how the insulation system is today, the day that you're testing this insulation system. And basically, this tan delta as a function of frequency can be represented basically by the ratio of the complex permittivity from the imaginary component to the real component. And you can see here both, right, the real component, the imaginary component, and between these two, they create this tan delta dielectric response, which is unique of the condition of that transformer, and is like the same thing like a power factor at line frequency, is temperature dependent. With that being said, we need to remember that different materials have different properties. And one of the most important things that we have here is that with this dielectric response, we can discriminate between the influence of the liquid insulation and the influence of the solid insulation. Each one separately has its own properties and its own characteristics. When we look into the system per se in a power transformer, right, we have about 80% of the insulation, or 90% of the insulation is liquid insulation. About 10% is solid insulation. Interesting enough that the effect of temperature on this insulation is not changing drastically the shape of the curve. And this allows us to apply the individual temperature correction factor, because when we look into the changes that could be on the horizontal axis by frequency or by magnitude on the y-axis, we can easily convey that information into the Arrhenius equation. And you can see here that we have the x-axis, the y-axis, and basically based on this and based on what is more important, which is the activation energy of the material, we can properly estimate based not on the reference table by nameplate, but on the condition that you have tested immediately, right, when you're running this test on your transformer. And that condition is not going to change. What is critical here again is if you want to go from 30 degrees C to 20 degrees C, I have seen majority of the mistakes in the field is measuring that temperature. Because sometimes the temperature gauges are not accurate, because sometimes the transformer has not been immersed in oil, because they drain the oil for, say a tryout process. So be careful about the temperature. The better you provide the temperature to the system, the more accurate the system will give you the assessment. And you can see here in this example, what I'm presenting here basically is the same material. This is craft paper at different temperatures. And you will see how from 20 degrees C all the way up to 80 degrees C, there is a shift to higher frequencies as higher temperatures come up. When we look into this, basically you can see that at 60 Hertz, you can see the red line, the dotted red line that I have right now, the 20 degrees C value, it's higher than the 40 degrees C and even higher than the 60 degrees C. But it's lower than the 80 degrees C at 60 Hertz. Why? Because that is the dielectric response that we have from that specific model or that specific example. So from this sample taken and elevated the temperature from 20 to 40 to 60 to 80 degrees C, you can see that the same point corresponds to, in this case, the 60 Hertz corresponds to 10 Hertz at 60 Hertz, at 60 degrees C, I'm sorry, or corresponds probably to 2 Hertz at 40 degrees C. It corresponds to another lower value in frequency on the 20 degrees C. That's the way that the information is being translated, and that's the way that we can estimate properly the individual correction or the temperature dependence of that insulation based on the Dfr measurement. So looking, of course, into the main applications of Dfr, that is power and distribution transformers, major influence on that area. One of the most important things to say is many people has been asking, how do you compare the Dfr results when you determine moisture of the solid insulation, right, versus other procedures that we have in place? Well, one of those is Karl-Fischer titration, and I think that most of the work that has been done to determine the database for the analysis is based on Karl-Fischer titration. But how many samples are you going to take out of your transformer? If you look at this example that we have from a SIGRA report, right, you can see that you can go from 1.1 to 4.6%. So different, the distribution of moisture in a transformer is not homogeneous. So you may need a big number of samples destroying the insulation system, because now it becomes a destructive test, right, to start taking samples, trying to get an average value of the contamination of moisture inside that solid insulation. And that is the beauty of Dfr. When we look at the bulk insulation, I cannot pinpoint you with Dfr that specifically in this point you have 3% of moisture, or in this point you have 2% of moisture. No, we cannot do that. But we can tell you that the bulk insulation of that transformer has 2%, 1%, 1.5%. So from here, as I said, the beauty of dielectric frequency response mainly is that we can discriminate between the condition of the solid insulation, right, and the condition of the liquid insulation, because we can determine the conductivity or the power factor dissipation factor of the liquid insulation. What is the advanced approach on dielectric frequency response? Of course, ITC, individual temperature correction, which allows you for a conversion from the frequency domain, right, power factor as a function of frequency, to the temperature domain, which is power factor as a function of temperature. And of course, if there are non-typical responses, we can look into contamination. And that could be one of the things that we may want to look at, that at 60 Hertz, you will not see. And narrowband DFR will be the first one to trigger that information if there is contamination. That is one of the key advantages. Now, you want to know exactly what's going on with that system, then you go into a third step to be a definitive test, which is DFR. So again, every material has different characteristics, and we can see here that, especially because we're talking about solid insulation, the relative permittivity of pure cellulose is about 5.6. If you look into dry paper, it will go between 1.5 and 3.5, and the relative permittivity of mineral oil goes between 3.1 and 4.5, depending on density. And when you look into just the oil, the typical relative permittivity mineral oil is about 2.2. So every single material has different conditions. And of course, you can see the difference between this crystal clear brand new oil and this oil that might have been already gone through quite a few years of service. So of course, the condition now here, the resistivity and the conductivity, of course, if you want to see on the other side of the oil, has to change. So the properties will change, and this will influence the dielectric response that we look at. With this being said, let's look at the response of just oil. So when you're testing only oil, what you will get is basically a linear response on the logarithmic scale. What is interesting about this, if you look at the very high frequencies, you have a very low dissipation factor. And if you look at the very low frequencies, you have a very high dissipation factor. When we look into the paper, to the contrary, this is very interesting, because you will see that the typical characteristic, the dielectric characteristic of the paper, you may have power factor values, similar power factor values at two different frequencies, right? And this is very important for you to understand. And then you may have a low value of losses at higher frequencies, but as compared to the liquid insulation, it's much lower, right? The losses that you have at very low frequencies. When these two materials get together, okay, let me just erase this quickly. When these two materials get together and we have now oil impregnated paper, we create the typical response that we see on a power transformer. And this is kind of an inverted S shape, right? But what does it mean? Now I have a curve. So now I need to do some interpretation of this curve. How do I look into this curve? So basically, we have differentiated different regions on this dielectric response. When you look into the very high frequencies and very low frequencies, the predominant influence is based on the paper, on the solid insulation. It's not only solid insulation, but the predominant influence is the paper. When we look into the middle range of frequencies, that is predominant influence of the oil. And when we look into the interface between those two, is basically what we look into the geometrical influence of the insulation system. We're going to talk about that in this slide. When we talk about the XY model, and just for you to have an idea, we're looking into the spacers and the barriers that we have in a typical interwinding insulation. Most of the time, and when possible, we're going to look into some of the hookup diagrams that we have. But the idea for us is to look at the interwinding insulation, where we have a similar construction of the interwinding. We look into the spacers, we look into the barriers, we look into the liquid insulation, which combined from this three-dimensional system, in reality, we look into these converted into a two-dimensional system in the XY model. And that way, we look into the capacitance or the complex permittivity of each material, right? And based on that, we do our complex analysis, which is basically this equation here. Now, one thing that I consider important to highlight is that DFR uses the XY model, right? If you have that information, and typically that will be only probably the manufacturer who can provide that information on the XY parameters, but it's not fundamental. The system, the mathematics, the modeling part behind the instrument are designed to use different different values, right, for the modeling purpose. So the most important thing for DFR, of course, and the mathematical modeling is to estimate the moisture content in the solid insulation, the liquid conductivity of the insulation liquid, and of course, detect any kind of degradation and non-typical responses. When we get into the mathematical modeling, right, just imagine that all this information, right, has different values and different variables or parameters in the equation. You can look at the equation here, right? This is what we use to do our modeling. So we have normally fixed values. That will be the liquid insulation relative permittivity, like we were talking. If we're looking into mineral oil, we're talking about a 2.2 value. We need to know the thermal activation energy of the solid and the liquid insulation, and we need to provide the temperature at which the insulation is being tested. What are the variables here? As we remember, the output of this test is basically the insulation conductivity and the moisture in the solid insulation. This is where we look into the geometrical part as a fixed or variable within limits. So the system provides limits depending on the type of construction of your transformer, right? If you have a core type or you have a shell type core design, right? If you are a manufacturer, you can use your engineering design values and provide that directly. Okay, so with that being said, let's go back to the power transformer and the test itself. The winding configuration and the measurement setup, we always try to look into the interwinding capacitance for the analysis. As I mentioned before, because we're looking into this XY process in the modeling part, so we will look into the Ust test modes. Normally, that will be your high to low, your high to tertiary winding, or your low to tertiary winding. Right? Those are recommended for moisture assessment. Make sure that you don't have any kind of electrostatic shield in between those windings, because that, of course, will give you some erratic numbers. One thing that we need to take into account is that basically the hookup of DFR test is exactly the same one as what you use for power factor testing. So when we look into a 2-winding transformer, as you can see here, if you need to run a CHL test, that is the recommended, because that's the interwinding insulation. So that's the test that I want to use to determine moisture. And then you have supplementary tests, which will be your CH and your CL. And there's many people asking always, well, if I determine moisture with CHL, why am I doing something with CH or CL? And the simple answer is just to make sure that you have a dielectric typical response, that you don't have any influence of contamination, that there's no dielectric issues that we could capture and prevent for failure. So that is our 2-winding transformer. As you can see, basically it's the same configuration that you have for power factor testing. If you look into an auto transformer, a single-phase auto transformer, basically this is one of the cases where you have to go high to ground, of course, and this is your CH capacitance, basically going from your all the windings together with respect to ground. When we look into the 3-winding transformer, you can see that now it becomes probably a little bit more complicated, because now you're looking to interwinding capacitances, which are recommended, and those that are supplementary. So you can go into all of those, and the moisture analysis should be very similar between those. So let's look into the things that are different between power factor and dielectric frequency response. The first thing, the frequency. Yes, power factor line frequency means that you're testing either 50 hertz or 60 hertz. And actually, we do not test at 50 hertz or 60 hertz because we try to avoid the noise that will be at the line frequency. So we will go 3 or 4 hertz up and down between the line frequency and get the specific value as an average of those. And then we look into the DFR test, which is a variable frequency that typically goes from 1 kilohertz all the way down to 10 millihertz or 0.1 millihertz. What about the voltage? As I was mentioning to you, power factor is typically at 10 kV, but we have to be careful about this 10 kV. I think that Ken answered to one of the questions saying, we do not want to stress the insulation. Sometimes people says, why do I do the test at 10 kV? It's because I want to stress a little bit more the insulation and have a better effect on my dielectric test. You use 10 kV for a 500 kV winding, and you're not stressing that insulation. So the reason for doing dielectric test is to measure the dielectric properties of that insulation system, which are your power factor, your capacitance, your permittivity. So those are the parameters that you're trying to measure. 10 kV is because you want to overcome any noise that you may have in the substation affecting your measurement. So it's basically an application of signal to noise ratio. But when we look into DFR, we only apply 140 volts RMS. If we are located, and this chart is taken from the DFR guide published by IEEE, and you can see that it's stating here that if you are working on a high electromagnetic induction location, high voltage DFR might be used. Okay, and the reason is because there's high voltage dielectric frequency response test that can be carried out at 2 kV. Then the measurement time, of course, when you do a power factor test, is seconds, right? With Delta 4000 or tracks, we can do all the configuration on the high voltage side, high to low, high to ground plus high to low in less than a minute. But when we're talking about DFR, as I said, frequency is proportionally inverse to time. So if we're going to millihertz, that might take some time. But we need to look into this because the frequency, when you stop the test, is dependent on the temperature. And that is very important. If you're testing at high temperatures, then you don't need to go very low frequencies. But if you're testing close to 0 degrees C, then you will need to go to very low frequencies, okay? Then the analysis, basically the analysis on power factor is based on trending and standard references. When you look into DFR, is instantaneous modeling. So it's what you have at that specific time. What is the objective of the test? It's used to identify general contamination of insulation. And that is, I would say, the key word here, general contamination of insulation. Because if you have a high power factor value, the next question is, okay, so what's wrong? Is that my liquid insulation? Is that my solid insulation? Is that contamination? Is that partial discharges? What is the problem? You get the trigger. And then when we're looking into DFR, you're definitive on your assessment. It's either moisture or it's, well, you can say the problem is in the liquid insulation or the problem is on the solid insulation. The other thing that you have to remember, and I've been trying to emphasize here the influence of temperature. So the time, if you are getting into a test, right? Typically, let's say your insulation, you have disconnected your transformer because this is an offline test, same thing like a power factor test, right? And that transformer has been sitting for, I don't know, some time. If you are in a location where the ambient temperature will vary between 20 and 40 degrees C, so maybe you might be in this range. So you may need to go, if the insulation temperature is around 20 to 30 degrees C, you will have to go down to 1 millihertz, and this 1 millihertz to go down to that one will take about 22 minutes. If you are on higher temperatures of the insulation, you don't need to go to that lower frequency. You will go only down to 2 millihertz, and that will take only 12 minutes. So, but if you guys go to Canada to do some testing, well, I will suggest to take a jacket with you because it will be cold, okay? So this is our dielectric response, okay? So we performed the test, we had some time, and this is what we got. So what is it telling me? Now I got a curve, and basically I'm looking into some result analysis. I got my power factor says that when I tested at 22 degrees C, for example, here, I got the capacitance is 4,084 picofarads. My dissipation factor was 0.38. And now that I'm correcting that to 20 degrees C is 0.385. my moisture is 2.7, the conductivity is 0.6 picosiemens per meter. So is that good? Is that bad? And that's the reason why in our system, we have incorporated what we call the traffic light assessment. And based on that, you can determine if you have good results or bad results, right? And you see, we have the traffic light looking into as new, good, deteriorated, and something to investigate. Think that in any standard that you will see, right, none of those standards says scrap the unit and just throw it to the trash can. All of them, when they reach a limit that is that basically shows a potential risk on the operation, they will say investigate. So that will go into further investigation. You may need to dry that transformer. There are different things here. So just so you know, the assessment is basically followed by this traffic light assessment that allow you to say this is good, this is bad. And if you have a curve that is non-typical, like what we're seeing here, you may have something like, let me try to draw something here right now, like this, for example, or something like this. I will suggest to give us a call and talk to one of our TSG guys in Dallas or somebody else in Megger to help you with the analysis of that kind of result, because now we will not be able to match exactly for moisture. This might be related to contamination. This might be related to some other process in the test. Okay. With that being said, at the end, what you're expecting is basically to have a report. And you can see here that your report will tell you all the information about the company, all the information about the test, all the information about the insulation and how that was assessed. So you see basically the same table for saying good, bad, or deteriorated, or investigate is right there. You will have as well the information of the test and the plot. With that being said, and especially when we start looking into some non-typical responses, there are different factors that will influence our DFR measurement. That is important for you to see. I'm making this reference, and that's again taken from the standard that was published just on 2018. You can look into the static shield. There might be some bushing surface influence, non-homogeneous oil, dirty tap changer, some winding design, cellulosic material, etc., etc. So because the information will get to you later, this is a table that will be important. If you see any difference, any discrepancy or mismatch against the modeling system, it could be because of the influence of one of these. The other main application, of course, if we are talking about transformers, is DFR on bushings. And Sanket already made some interesting application looking into the narrowband. So if you can make that much assessment with narrowband, just imagine all the things that you can do with a full dielectric response for high voltage bushings. And one of the very first things that you can look at is like in this example, you have 4 bushings, right, on the high voltage side, and this was tested at 31 degrees C. And just by looking at the image, without going any further into any analysis, you can clearly see that these 2 bushings have low losses, lower power factor on this axis, and these other 2 have a high discrepancy on their power factor values, right? All the dielectric response shows much higher losses. So there might be something going on that we need to investigate. When we do the analysis, and I was telling you, we can go from the frequency domain into the temperature domain. I look into my bushing H1, just so you remember, H1 is one of these high losses bushings. Look at the thermal response. It's telling me that from 20 degrees C going higher, right, I will have a higher power factor as well. And you can clearly see, because of the application of this individual temperature correction, that now I can have the information at 30 degrees C, and I have directly from the system the information at 20 degrees C, which is this red line here. And that is very important. Now you see, for example, on the good bushing, H2, completely different thermal response, of course, because the condition, the dielectric response is completely different. Therefore, the thermal response will be completely different. And you can see now that especially on the 60 Hertz line, the response is very flat. So there's minor discrepancy, minor changes when we look into this shifting to higher frequencies or to lower frequencies depending on temperature. And that's the reason why your temperature dependence is almost linear. There's a very little slope in this case. So as I said, it is very important to be able to monitor what is the dielectric response of that specific piece of equipment that you're testing. And of course, one of the problems that you can face with trying to do a low voltage test is if you go to a high electromagnetic induction area, right? And you try to run a low voltage DFR test. Noise is something that we cannot avoid, right? The only thing that we can do is minimize the effect of noise in the substation. And one of the problems that we have here is because if you compare your power transformer, you're talking about nanofarads insulation. But if you're looking at the bushing, you're looking into hundreds of picofarads, maybe 300, 400 picofarads for your bushing. So that makes a big difference because you're looking into measurement of current. What do we do in this case? We use an amplifier. And what we typically will do is the Idax unit will do the test at 140 volts RMS, but the amplifier will multiply that 10 times. The only thing that we need to do is to select in the software to use an external amplifier, and that's it basically. You have amplified 10 times the excitation signal for your test, and that becomes much easier. Let's look at some examples here. These are examples of different testing. This was on a 500 kV, 600 picofarad bushing. You can see at 140 volt, you get this swing on the dielectric response. And you have to be careful because I've seen sometimes that people try to smooth that or try to make an analysis out of a non-typical curve, and that may bring you into misleading assessment. But when we tested this at 1400 volt, you have a perfect shape that could be easily analyzed. Same thing on this example here. This is an 800 kV bushing. The first response in red is what you see under the influence of noise because of low voltage, and then just cranking up more voltage, you can see that we overcome the effect of noise, and we have a very good and smooth dielectric response that could be properly analyzed. So let me show you right now a little bit on how to operate the Idax unit. There we go. Okay, so basically this is the setup for the Idax software. You can select moisture, you can select different type of testing. You have a single test, you have multiple tests, or you can use a previous test as a measuring template. Typically, we're going to look into a simple example, which is our two-winding transformer. And you can see all the options that you have for that two-winding transformer. So you can do a CHL and CHG test simultaneously, right? When you have two electrometers, you can do two measurements at the same time. So if each one takes 20 minutes and you do that separately, it will take you 40 minutes. But the capability of the instrument allows you to do two measurements simultaneously. And that will help you, of course, improve the efficiency in the field. You don't want to spend much time in the field. So by having two electrometers, of course, that makes a big difference in time. So basically, what is important here? Temperature, and not ambient temperature. I really not very concerned about the ambient temperature. What mainly concerns me is the insulation of the object that you're testing. Look at this. Every time you select a test, you have a hookup diagram. So it's very easy to follow if you're doing a bushing test, an interwinding test, whatever test it is followed and it's indicated in the system with the graphic, the hookup diagram connection. You select the unit to connect. Typically, the connection is via USB or via Ethernet. So you have two ports in case one of those fails for whatever reason that is. On the settings, you can look into all the information. Typically, we select the multi-frequency measurement below 0.01 hertz, so you can speed up the measurement. You will be basically testing 3 frequencies at a time. You select what type of generator you're using. If you're using just the Idax, you use 200 volt peak. And there you go. One of the interesting things that we have in the system is the oscilloscope. And you can see the red sinusoidal is what represents the voltage that you're applying. The white one is the measurement input, and the green one is the current flowing through ground. So at this time, you're basically running 2 tests at a time. You can see on the left-hand side that we have here, you're testing basically your CHL and your CHG at the same time. You're not running 2 tests separately. It's at the same time. And now, as soon as you cover a certain portion of the frequency range, right? You see all the changes that are going on in the system, right? The measured frequencies and the time, till you get the final dielectric response, and immediately you get the assessment on the bottom. What else can you do with the Idax unit? You can do also just a power factor test, a dissipation factor test, right? And you will select the capacitance that you want to test. You just execute the test, right? And you see that we basically takes about 7 seconds to run your power factor test. You can see the oscilloscope again, right? You have 1 voltage signal, which is the red, and you have 2 currents, because in this case you will be testing for 2 capacitances. And then also you can look into the ITC. ITC is very specific for bushings and instrument transformers. And you can select the type of insulation that you have on those, if that is on oil impregnated paper or resin impregnated paper or whatever that is. And you can see again, if you're selecting the bushing, you have the configuration and you have the hookup diagram. When we're testing the bushing, again, you can see the oscilloscope starts getting the information. You go from 1000 hertz, but you selected ITC. So you see that basically you are drawing 2 plots at the same time. Because the temperature selected is 30 degrees C, the curve that you have on your right-hand side represents the higher temperature, and that is the one that is being measured. And in parallel, we can see the ITC corrected response at 20 degrees C. So basically, you have in one shot the information and the corrected curve for proper analysis. You can see here that we can also do a DC test. When we look into the DC performance, we can look into the polarization current and insulation resistance. And if we want to do a polarization index test, then we're looking into 600 seconds, which corresponds to 10 minutes, right? And we basically, with the same unit, we are doing moisture analysis, we're doing power factor testing, we're doing ITC, the temperature correction. We're looking into the DC response as well, right? So we're looking into frequency domain as well as time domain. And you can see basically here you have your polarization current and you have your insulation resistance. As soon as you pass the 1 minute on your test, basically you can see the resistance going, you can see the current, the polarization current here. And at the end of the test, of course, what you get out of it is the information related, right, to the insulation resistance, dielectric absorption ratio, and polarization index. You can see those values are being populated as the test continues. When you're done, basically you can look into one additional feature that we have in the system, which is dry out. We had a dedicated webinar talking about dry out. So just so you have an idea here, what we're looking is into factory dry out and how to monitor that continuously. You don't want to bake too much that insulation system. You don't want to get it raw out of the oven. So this is the way that we have all these tools integrated in the software for Idax to look into the dielectric assessment from time domain, frequency domain. I mean, it's the most informative tool that you have for assessment of power transformers from the dielectric point of view. With that being said, let me talk a little bit about Idax 300. And the product itself has more than 20 years in the market. Not this version that you see right now here. The very first unit in the market was the Idax 200, right? And that was a little bit of a bigger unit, of course, 24 years ago. With time, technology, power electronics, communication, computer sciences, we have been working on this technology for the last, as I said, more than 20 years. And there's so much information that we have learned from the dielectric frequency response testing. This is basically state-of-the-art measurement of moisture content, tan delta, power factor, oil conductivity based on this frequency domain response. It's very easy to use. As you could see, the software is pretty much automated, and it gives you the information, provides you with assessment, has this traffic light interpretation of results. It has dedicated test procedures for power transformers, bushings, current transformers. And there's one, actually, I really like to have the option of a general specimen where I can do whatever I need and the way I need, the capacitance that I need. If it is a GST or a UST mode, I mean, I have the opportunity to do any kind of test on any type of insulation system. It comes with the automated individual temperature correction ITC, and that's what I said, that if you don't have the delta and you don't have the tracks, you can always use the Idax. And of course, the measurements are quite reliable, even under high interference, and that's the reason why we have the amplifier as well that will allow you to do tests at 2 kV. And interesting enough that sometimes people will say, well, why do you need to do a test of insulation resistance at only 200 volt? Well, now that you have an amplifier, you can do the test at 2 kV, which becomes much more interesting. One thing that I want to highlight about the unit, because sometimes we have customers all over the world, and sometimes in very remote locations, and Idax can be calibrated on site. So Idax comes with a calibration box and with the proper procedure that is provided with the calibration box. You as an end user in the field can do the calibration. You need just a very accurate digital multimeter to do the calibration, and you can have your unit calibrated on site without the need to send it out to our factory or anything like that. What we need to certify is the calibration box. So while you don't need to lose time sending the unit to factory, you may need just to send the calibration box, and we will certify that in our factory. So basically, just to summarize what we've been talking about DFR, the most important thing here is to determine moisture concentration in the solid insulation, then conductivity of the liquid insulation. Then we look into non-typical responses. And again, non-typical responses might be derived because of degradation of the insulation, might be because of improper testing. So when you get a non-typical response, please get back to us. We will be more than glad to assist you with that. And again, from frequency domain, we can go into the thermal domain, right, into the thermal response, and look at the power factor as a function of temperature. And that is a unique feature that we provide. So you can see that there's no table that will really correspond to what the insulation condition is the moment that you are testing. And the other thing, something that Sanket was showing on some of the secret values, they are showing numbers for different frequencies, which are limits valid only at 20 degrees C. And my question is, how many times any of you listening to this webinar has tested a transformer or a bushing at 20 degrees C? I'm pretty sure that it's very difficult to be that moment exactly when the temperature was 20 degrees C. I'm talking the insulation temperature. So you're always off that temperature by a few degrees or by a lot of degrees. No matter what temperature you're looking at, especially if it is above freezing, of course, you can do the individual temperature correction and have a very good assessment, right? And the true thermal response of the insulation based on the dielectric response, the unique dielectric response that it has at that specific moment. So again, with the advanced features that we have for dielectric frequency response, you can apply 2 kV for dielectric frequency response in the same frequency band, going to from 1 kilohertz all the way down to 0.1 millihertz. And you can do the narrowband DFR, you can do individual temperature correction, and you can apply multi-frequency test mode. I need to to add to this list, basically, that you can use not only multi-frequency test mode to speed up the test, but also you can use 2 electrometers at the same time, which will, shorten the time absolutely, because you're testing 2 capacitances at the same time. Look into the references, right? There's quite a few references: SIGGRADE 254, SIGGRADE 414, the latest publication from IEEE, the guide for DFR testing, which is C57161. This technology is so important now in the industry that we are working in the IEEE Transformers Committee to develop the DFR bushing application guide. So just some of the references that I was talking about. I want to highlight in the IEEE guide that there's lots of good information here, especially on the annexes. So please look into that information if you have access to the IEEE standards. Otherwise, just go to the IEEE website and you can purchase that guide. And here's my contact information. Always glad to hear from you. If you have any comments, or if you have any specific or special application for dielectric frequency response, I will be more than glad to assist you, as well as my dear friends from the technical support group in Dallas, Texas. So here's the email address for the technical support, as well as the phone number. And Mike, if we have any questions, bringing it back to you.
Yeah, now would be the time, exactly. So the second portion of our seminar has concluded. We're going to jump into the Q&A segment real quick. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a brief survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future seminars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of the presentations, certificate of attendance, along with a link to the video recording of this seminar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars. Be sure to join us tomorrow for the second day of our virtual Substation Best Practices seminar. All right, so let's jump into your questions. The first one I have is going to be for Sanket. Sanket, where do you use the VAX 220 and the VAX 230 that can do a DFR test for up to 14 kV all the way over to 20 kV?
So as Diego mentioned, sometimes you might be testing in high noise environments where there's a high amount of EMI, and that can influence, that can cause noise in your DFR measurements. In those cases where you want to apply a higher voltage to overcome the noise level, in those cases you would use the VAX to amplify the voltage and to test at a higher voltage.
All right, thank you. Dinesh, would PF measurements from Idax match the 10 kV PF measurement?
That's an interesting question. Typically when you perform the test using Idax, the DFR measurement, it also gives you the 60 hertz power factor value, and in some other parts of the world it might be 50 hertz. But it does give you a 60 hertz power factor value, and the question basically is about, are power factor values voltage dependent? For a oil plus paper kind of insulation, your power factor value should not be, in theory, should not be voltage dependent. So if you perform the test at 140 volt with Idax, and then you perform the test at 10 kV with your traditional 10 kV power factor test set like Delta 4000, your reading should be very, very close to each other. The only cases where you might see a discrepancy in the measurement is when you are testing in a EHV station like 500 kV yard, 765 kV yard, where because of lot of external interference, because of overhead lines or some grounding problems, you might see some discrepancy, because you are talking about, at the end of the day, you're talking about signal to noise ratio. If you have a higher signal, then you have higher capability of suppressing the noise because of better signal to noise ratio. But as I said, like in theory, and for majority of the cases, if you're working a 138, 230 kV yard, your Idax 60 Hertz power factor measurement would match with the 10 kV power factor measurement.
All right, thank you. Dr. Robolino, does FR3 oil affect the DFR test?
Okay. If we look into the effect of FR3 on the DFR test, there's no effect per se on the test itself. Now, the results that you get from FR3 will be different as those from mineral oil. You have to remember that the dielectric properties of FR3 are different from those of mineral oil. Just to give you a quick example, we were looking into the traffic light assessment, right? For mineral oil, if you look into 0.3, 0.4 picosiemens per meter, that is a very good condition. That is kind of brand new oil. But even at somewhere around 10 to 12 or 10 to 15 picosiemens per meter on the conductivity of FR3 is very good. So there's differences not on the test, but on the interpretation of the result. Okay.
All right, thank you. While I have you, the next question is also going to be directed for you. For DFR, some people think more voltage is better to the test, but how does voltage affect the measurement? And what is the recommendation for DFR voltage tests?
Okay, so basically, if you are under normal conditions doing your typical UST test to determine the moisture in the power transformer, and you have a big capacitance, the only thing that you need is 140 volts RMS, right? So that's the typical Idax. But I think that if you look into some of the C-grade reliability reports that we have on the technical brochures, you have seen the influence of bushing failure on the overall failure of a power transformer. And that's the reason why now more than ever, the dielectric diagnostics on high voltage bushings is quite important. If you are in a high interference environment, you will need to crank up the voltage and apply higher voltages. And that's the reason why, especially for low capacitance, and again, for low capacitance specimens, like bushings, like instrument transformers, like CTs or PTs on substation, what is suggested is to apply higher voltages. In this case would be the 2 kilovolt peak or 1400 RMS volts. Mm-hmm.
Thank you. Additionally, is it possible to use Idax to do VLF measurements on MV cables?
Okay, we don't need to mix maybe two different concepts. VLF, you can do 10 delta VLF, of course, but that typically for XLPE cable is a very low frequency, like 0.1 hertz, being applied to the insulation of the cable, but you're trying to go and stress the cable. So you're looking into the nominal voltage of that cable for the VLF testing. So when you do Idax, again, you're working into the low voltage side, right? And I would think that Idax plus the VAX 220 or the VAX 230 is the tool to go for medium voltage cable. That way you can go on voltages up to 20 kV, 30 kV.
All right, thank you. Dinesh, what is the recommended frequency range for DFR tests?
That's an interesting question, and as Dr. Diego was pointing out, that this is a full DFR test that that we were covering in the second portion of the BPS. If the range of the frequency is dependent upon what is the insulation temperature. As you know that as you go lower in the frequency range, it's going to take longer time to perform the test. And the higher frequency is kind of fixed at 1000 Hertz, but the lower frequency is dependent upon what is the insulation temperature. For instance, if you are in the range of 20 degrees C or 30 degrees C, then you may only need to go up to 5 millihertz. But then if you're working in a colder environment where the insulation temperature is in the range of 5 degrees C or 8 degrees C, then you may have to go to 2 millihertz or 1 millihertz. One of the nice things that the Idax software has is that when you enter the insulation temperature, it would automatically define the lower range of the frequency. So that way you don't have to worry about what frequency range you need to pick to get correct moisture assessment of the insulation under test. So from that point of view, it's a great feature available in the Idax software.
All right, thank you. Dr. Robolino, what are the assessment limits taken from?
That is a very good question, because there's lots of information on different standards talking about the limits of moisture in the liquid insulation and how those are correlated to the insulation through equilibrium curves, for example, in the paper insulation. So mainly, if you look into the standards, none of those is directly talking about moisture in the solid insulation. I think that there was one occasion when we were looking into one specific reference for different kind of GSU transformers, and the only reference that we were able to find was on some specific literature for nuclear power plants. But besides that, the majority of the information is taken from the correlation of the limits on the liquid insulation with respect to the solid insulation. Mm-hmm.
All right, thank you. And while we have you, Dr. Robolino, can you perform hot collar tests with the Idax?
Especially if you have the 2 kV system, why not? I mean, the same things that you can do with your power factor test set, you can do with Idax. Idax, again, is a different approach talking into the dielectric frequency response analysis, but you can do your power factor test like we were showing before. And of course, you can do a hot collar test as well on lower voltage, right? Typically, you try to do your hot collar test at 10 kV, depending on the rated voltage of the bushing, but you can do a 2 kV as well and have a reference value. In this case, you're not looking into power factor values, you're looking into current and watt losses. So that is the answer.
All right, thank you. It looks like that's all the time we have for a question and answer for this session, unfortunately. We apologize if we didn't get to your question today, but we will be following up with you offline in the next couple of weeks. But I'd like to thank you all for attending. If you would, please remember to answer the survey. That survey will include a field for you to request a quote or a demo if you're interested. Thank you all again for attending, and I hope to have you join us tomorrow for the second day of our virtual substation best practices seminar.
Thank you very much.